Good job, man.
Our first speaker is David Gepner, who's going to talk about Thom spectra and twisted umkehr maps.
Well, I first want to thank the organizers for throwing such a great conference and more generally for this fantastic semester at MSRI. It's really been a pleasure to be here, so I think we owe them all a round of applause. And I apologize to Andre if he wanted to be the one who did that, but I'm sure he'll do it again. So given the title of the conference about reimagining the foundations of algebraic topology, I thought I would talk about a project which involved exactly some reimagining foundations, namely some joint work with, well, first with...
David, is that the backboard?
I was going to write on it. Is that not okay with you, Sean? So first some joint work with Blumberg. Okay, I already screwed up the alphabetical order here. Ando, Blumberg, myself, Hopkins, and Resk on generalized Thom spectra, and then further work with Ando, Blumberg, and myself on multiplicative properties of these and twisted umkehr maps. So why do you care about Thom spectra? Well, they're important in algebraic topology for a lot of reasons. So classically, they arise in the following way. We have some group G that maps into GL1 of the sphere, which we can imagine as, if you don't know the definition, think of it as the homotopy automorphisms of the sphere spectrum. And with this we can form, it wasn't exactly stated like this originally, but we can form the homotopy coinvariance, or the homotopy quotient, S mod G, where G is acting via this map to GL1 of the sphere. And this is the Thom spectrum, MG. So you've seen a lot of these. I'm sure everyone in the audience has seen numerous examples of these. So, for example, well, if we take point into GL1 of S, we just get S itself under the guise of framed cobordism. More computable is if we take the infinite orthogonal group mapping to GL1 of S via the action of, say, ON on the pointed end sphere Sn. This gives this. So these are compatible as n varies, and it gives an A infinity map. It's actually E infinity. Maybe I should say that. E infinity map from, well, this one, with associated Thom spectrum MO. And there's all these connective covers of O. We have SO, we have spin, we have string, and, well, I'm told there's even a further connective cover of interest now called 5-brane. And these give interesting and sometimes computable, partly interesting because they're often computable, Thom spectra. So M string, I'll just write in M in front of all this as such. Okay, although maybe the most well-known example is we also have U, the infinite unitary group mapping to GL1 of S via UN acting on the 2n sphere. And we get MU. Now this one is famous, especially because its homotopy groups are so nice. It's isomorphic to the Lazard ring. And through this connection, we get a connection, we get the connection between formal group laws and complex orientations. Which are ring maps from MU to some homotopy commutative ring spectrum R. And there's, of course, this has played an essential role in modern algebraic topology. Okay, so so far no foundations have been reimagined, but thank you, John. See, I should have put these down before so you would have wondered if I had some fantastic diagram drawn behind them. But yeah, I think everyone knows I would be way too lazy to do that. So how do we generalize this? So another feature of Thom spectra is that they sort of come up in the theory of twisted homology and cohomology. And we want a slightly more robust notion of them that we can fit into a lot of other contexts. So that's what I'm going to talk about today. And I'm going to use the theory of infinity categories. Not only because I like it, but because it actually adds quite a bit of, you'll see that certain adjoints that you might want to construct are kind of hard to construct on the level of models, but they are easy to construct on the level of infinity categories. It's not really formally any different, but you don't have to play around with model structures and changing model structures. Let me give you sort of the main example of this. So I'm going to let script S denote the infinity category of spaces, which we also sometimes call infinity groupoids, following the homotopy hypothesis that Chris mentioned in his talk. And if you want a specific definition of this, you can take the nerve of your favorite model category of spaces, like topological spaces. This is now a quasi-category in the sense of Joyal, and you can invert some weak equivalences in the infinity categorical sense. Maybe that's not the most explicit definition, but the point is it comes directly from model category of spaces, of topological spaces and weak equivalences. So you have these slices. If I have an object in S, which I'll think of as a space, I can form the slice over X, which I'll write like that. So these are spaces equipped with a map to X. And this is contravariantly functorial in X via restriction. So, or you could think of it as pullback if you want. So if I have a map f from y to x, I get a map f upper star from s over x to s over y, which is the pullback. And one of the most useful things in this infinity categorical perspective is that f upper star has both a left and a right adjoint. F lower shriek and F lower star, respectively. So what I actually get then is I get a functor which I'll call S slice. You're supposed to think of it taking a variable there, but I won't always write that. I'll just write S over. And it's from S op, and, well, it lands in large infinity categories. But because it has these adjoints, and because these slice categories are nice types of infinity categories, are presentable, it actually factors through the category of presentable infinity categories, which I'll write this like this. And, well, maps that are simultaneously admit a left and a right adjoint, or rather, I should say, functors which are both left and right adjoints from this discussion. So what are the features of this? Well, it has a couple important features. So first and foremost, this functor, S under, from S op to, well, I'll just write it like this for now. This satisfies descent. This is a feature that you get in general in an infinity topos. And what does that mean? It means it's a sheaf of infinity categories on S with respect to the canonical topology. In other words, if I have X, and that's written as a colimit of some spaces Xi, and if you're thinking of these as actual spaces, then you want to think of this colimit as being a homotopy colimit. Then I get a canonical equivalence S over X to the limit of S over Xi. So that means it's a sheaf. It satisfies the sheaf condition. It's a sheaf of infinity categories. This might be an example of what you might call, perhaps, an infinity two topos, although I've never thought much about what that really would amount to. Another feature that it has, yeah.
So I guess I'm a little confused. It doesn't look like that follows from the universal property of a colimit directly because you're mapping it. So is there some reason to say why?
Yeah, well, I mean, it basically uses descent in the infinity topos. So the descent axiom sort of says if I'm given a space over X and X is built up from pieces, that space decomposes into the colimit of its restrictions to each Xi. It's not formal. It's using something. So each of these slices is symmetric monoidal via the fibered product. So if I put all this structure together, I actually get a sheaf, which I'll call S slice, from SOP to commutative algebra objects in presentable infinity categories where the functors have both a left and a right adjoint. So this is a lot of structure. This is, in fact, this structure amounts to what's called a Wertmüller context. In the sense of Fausk, Hu, and May. Question?
I was curious if maybe you get a larger function on a category of correspondences by using that.
Yeah, that's an excellent question. Certainly you could add some extra functoriality to this. So I'm not exploiting all the functoriality that I could. Yeah. Well, lower shriek is the push forward. It doesn't generally preserve products. Well, I'm defining this in a strange way. This is defined to be the objects are commutative algebra objects in PRL. And the morphisms are symmetric monoidal functors, which admit both a left and a right adjoint. The notation is a little bit misleading, perhaps, but I'm not quite sure how else to write it. So, more generally, well, let me say a third property. A third property is because S is freely generated under colimits by just the point. One of these sheaves, a sheaf, any sheaf of this form from SOP to this category is determined uniquely by its value on the point. So actually all of this data is exactly comes from a single symmetric monoidal presentable infinity category C, no matter what the sheaf is. So how does this work? Well, there would be, if I had told you this to begin with, you might be able to guess exactly what the functor is. So if I have such a C, then I can define C over X. Okay, so let me be specific. C is a commutative algebra object. Like before, and X is a space. I can define C over X to be functors from X op into C. I chose the op, well, because X is a space or an infinity groupoid. I can op it, and I get something canonically equivalent to X. So the op is optional here. Sorry. But I want to write it this way so I can think of it as C-valued presheaves on X, just as a handy mnemonic. And then, of course, given a map F from, say, Y to X, I have the restriction from functors from X op into C to functors from Y op into C. And this admits, this is symmetric monoidal. Because I'm just defining the monoidal structure here to be pointwise. And admits left and right adjoints. Which are just the left and right con-extension functors. But now you might ask, how is this related? So this is a question. How is this related to the original functor that I considered, the slice in spaces, in the case that C is equal to S? Well, again, we have this descent property, which says that, well, first of all, if X, so the answer, if X is a space, then X is equivalent to the colimit over the points of X of the point. That's another feature that you have in an infinity topos. So by descent, we have that X over X is equivalent to the limit from point into X of S over point, which is the limit point into X of S, which, if you think about it, is the same as functors from X op into S. So it's the same thing. I just rewrote it in the case of spaces, which I can do. I can identify this slice over X with functors out of X. And this uses the fact that I'm thinking of X as both a space and an infinity groupoid, which I can do equivalently in the infinity category of spaces. Okay, so So this Wertmüller context, so having a Wertmüller context gives lots of handy formulas. So if I have this sheaf like this, I can, where C, so it's determined by this symmetric monoidal presentable infinity category C, which, by the way, is automatically, just coming from the definitions, automatically closed symmetric monoidal. That's an application of the adjoint functor theorem. I get all kinds of formulas like for f going from y to x, I get things like, well, if I have, let me say I have m in C over M and N. Well, this might actually, let me just write it out like this. I'm going to write the tensor over X for the tensor product in C over X. This is equivalent to the pullback F upper star M tensor over Y with F upper star N, for example. So restriction preserves these tensor products. And while there's, maybe I won't list all of them, but there's all kinds of interesting conditions. Let me give a sample, like the projection formula, which I have written down as number 4 here. F lower shriek of F upper star of M tensor over Y with N is equivalent to M tensor over X with F lower shriek of N. All of this stuff follows formally from the setup that I've given. And, well, I wanted to label conditions 1 through 5, but you can consult the paper if you want to see what they actually are. I don't want to take the time to write them out. Sorry? I think that you need to use the symmetric monoidal one there, but I didn't think about that. But what I do want to say is if C is stable, in addition to these other properties, and F from Y to X is proper, just in the weak sense, that the fibers YX over each X in X are compact. I don't mean anything fancy here by just, yeah. Then F lower star admits a further right adjoint. F upper shriek. And this yields dualizing complexes in the sense that Vesna was talking about. Well, I didn't verify any finite injective dimension condition, but it really does lead to some sort of Grothendieck style duality here. That's a good question. I mean, probably, but you should ask Joyal, who's fortunately sitting right next to you. Okay, so what does this have to do with Thom spectra? Well, I'll specialize. I'm going to specialize C to being modules for A, where A is an E infinity ring spectrum. So actually, for much of what I'm going to say, you really only need En. Basically, for everything that I'm going to say, you only need En. But I think for the sake of simplicity, I'll just think of A as being E infinity. So, for example, I want to do a couple examples. I could take A to be the sphere, in which case C is just spectra. This is the infinity category of spectra. And then, so this definition of spectra over X, or spectra parameterized over X, is then by definition functors from X op to spectra, or if you prefer, presheaves of spectra on X. So it's a natural definition. This has a unit, which I'll call the sphere over X. And this is given by pulling back the sphere via P, the projection from X to the point. And it has a fiberwise over X smash product, which is its symmetric monoidal structure. And just to maybe give a little bit more intuition about what this looks like, if say, X is BG for some A infinity group G, then spectra over BG, well, that's functors from BG op into spectra, which you can readily check is equivalent to modules over the spherical group ring S adjoin G. So this is sort of the motivating, or this is what comes up in A theory in terms of the objects that you study or take the K theory of. But what does this have to do with Thom spectra? So going back to the general case now, well, okay, I guess I'll just keep specializing C to this for the sake of concreteness, but you don't have to. So there's an interesting observation that you can make, and it goes as follows. So we have the Picard functor from commutative algebra objects in presentable infinity categories, which, if you don't have an intuition for what this is, even though I've been using it for the past 15 minutes, I apologize. I mean, I should have said this before. You can think of this as being sort of nice symmetric monoidal model categories, such as modules over an E infinity ring spectrum. And this Picard functor, it goes to, well, commutative algebras in spaces, which are moreover group-like. So these are group-like E infinity spaces. And what is pic? Pic of C is by definition, all right, C cross, the space of invertible objects and invertible maps, but that's supposed to be implicit in calling it a space in C. And even though these are large categories, you can check that when I take pick of something presentable, it has to be small. So this is actually small. And the observation is that, so this is a theorem in a paper with Ando, Blumberg, and myself, is that pick has a left adjoint. And this left adjoint is presheaves.
Why would it be so if it took, like, say, S, right? So then I take all spaces and all equivalences. So what's my...
Well, these are the invertible objects. The only invertible
objects.
Yeah.
I'm sorry.
So pick has a left adjoint and it's presheaves. So how is presheaves symmetric monoidal equipped with the convolution, the Day convolution symmetric monoidal structure? That requires you to take presheaves on an E infinity space, or a symmetric monoidal category more generally, in order for presheaves to have this convolution symmetric monoidal structure. But in this case, we're considering the functor from here to here, so we have that. Yeah. Yeah, absolutely. Or connective spectra. It can be called any of those things. And so here PRL means just presentables and left adjoint functors.
Okay. Presentable and R left adjoint.
Yeah, and R left adjoints. So let me describe what does the convolution look like. So another name for presheaves, as we discovered, is spaces over a given space. So what does the convolution look like? Well, if I have y over x and I want to tensor it with z over x, what I do is I take the product that lives over x cross x, but then because x has a symmetric monoidal structure on it, I can multiply and get something over x. That's how this works. And then this is part one of the theorem. And then part two is that the counit of this adjunction so what is it? If you write it out, this is spaces over pick of C going into C is the generalized Thom spectrum functor. So this is, let me make a few remarks and explain a little bit about how this works. So first remark, C can be taken to be En for n greater than 0. You don't just need symmetric E infinity guys. There's an analogous result for En algebra objects here, and then group-like En algebra objects here, which are n-fold loop spaces. And, well, yeah. Well, let me make it explicit as follows. So this is part 1 of the remark. Part 2, for C equals spectra, pick C is pick of S. That's just shorthand for that. And that's Z cross BGL1 of the sphere. And then the classical Thom spectrum, well, it ignores the Z part, usually, and just looks at the part sitting in degree 0. So I should mention this functor is colimit preserving and symmetric monoidal, which kind of gives you a formula for how to figure out what it's doing in general.
I'm worried a little bit with the Z because conductivity is still preserved if you have the suspension?
Well, let me just say I'm writing this as I'm not displaying the E infinity structure on this. This is an equivalence of spaces. Just for simplicity. You can believe that BGL1 of S maps into here in a symmetric monoidal fashion. So then if I have X over BGL1 of, let's say X is BG, BG over BGL1 of S, this deloops to an A infinity map G to GL1 of S. And what this thing does in this case, and this map, I'll call it alpha, and alpha is sent to the Thom spectrum MG, which, as discussed before, is the sphere mod G via this action of G on GL1 of S. But the point is that we don't have to restrict ourselves to spectra. Any other nice category that satisfies the properties that I've been talking about will work equally well. I don't have to stick to BG either. I just wanted to write this formula.
So what would be, would you put back S1 to over BG and then you sum? Or something?
Yeah, you sum. Any X is a sum of things that look like BG, and then this gets sent. Because the functor preserves colimits, this gets sent to the wedge here. Okay. So even though I said it before over here, now I really want to restrict to C is mod A for A in E infinity ring spectrum. And, well, I can define the A twisted, well, cohomology of some space X equipped with a map to pick of A as follows. So I'm going to write X to the alpha for the Thom spectrum. I should say Thom A module spectrum of alpha, because it's going to land in mod A now, and not just spectra. And I'm going to define the alpha twisted cohomology, and homology is the following. So the alpha twisted nth homology group of X is then defined to be pi 0 of the mapping space in A modules from sigma n of A into the Thom spectrum X alpha, which is just the same as pi n of X alpha. That's the alpha twisted homology. And the alpha twisted cohomology is pi 0 of the dual construction. I take A module maps from X alpha into sigma n of A. And now I want to do some examples. So so let's say interesting examples of this construction. Interesting examples. Yeah.
Why do you need a degree now? Isn't the degree also a special case of it?
Yeah, just for concreteness. That is a correct statement. But so first, let's take A to be Ku, the complex K theory spectrum, and we have we have pick of Ku that receives a map from BGL1 of Ku. And we know that there's, we know what this looks like. I'm not going to write it as an E infinity space. I'm just going to say that this is, well, let me just say that you know that GL1 of Ku contains a copy of BU tensor, the multiplicative structure on BU, which, well, receives a map. So from BU1, except now I'm de-looping this, so I have B of BU, and I have B of BU1, which is KZ3. And this is the usual, you get the twisted K theory. Let's say K alpha star of X for X, a space, and alpha in H3 X Z. So some other examples that came up in Thomas's talk. So what about if I replace, oh, this works this works equally well for little ku. And there are analogs for big KO and little KO, except you'll be working with k z mod 2 instead of kz3. So what about TMF? Or, as Bjorn mentioned, we could also consider k of ku. Do we have any canonical twists here? Well, so there is a map from kz4 into both pic of TMF and pic of k of ku. The algebraic K-theory spectrum of the connective topological K-theory spectrum. And I thought I would describe these as an interesting example. So you have the this group B string, and it's basically defined as a certain connective cover of B spin, because B spin has a bottom homotopy group in degree 4, which you can kill by taking the map to KZ4, the associated Postnikov guy, and kill it to get the fiber is B string, and then if I take the fiber again, I get KZ3. So we also have we can form two Thom spectra now. We can form the Thom spectrum of the following maps. We can do KZ3 into BGL1 of the sphere, which is actually, I'm taking to be the trivial map to factor through the point. And by this map, this will map to the Thom spectrum of B string, mapping into BGL1 of the sphere, just because B string maps to B spin, which maps to BO, which maps to BGL1 of S, like that. And from this, well, because this Thom spectrum, the map classifying this Thom spectrum is null, we get this, that this Thom spectrum is just the suspension spectrum of KZ3, which is an E-infinity ring spectrum. This Thom spectrum is M string. And this maps then into, via the string orientation of Ando, Hopkins, and Resk into TMF. So this is adjoint. Maybe to be consistent with my previous notation, I should have written this as the group ring S adjoin KZ3. And because this is a group-like E-infinity space, this is adjoint to a map from KZ3 into GL1 of TMF. And I can deloop it to a map from KZ4 into BGL1 of TMF, which then maps into PIC of TMF. So that gives me a twisted elliptic cohomology corresponding to degree 4 homology classes of a space. So I get a twisted TMF cohomology TMF star alpha of X for any space X and alpha in H4 X Z. And the map to so that we have this other theory here, which also I claim admits a map from KZ4. So the way that you can see that is for instead K of KU. Well, so the underlying infinite loop space of K of KU is Z cross BGL of KU. And there's an E infinity map KZ3, which I'll identify with B of K Z mod 2, K of Z2, which maps into BGL1 of KU by the K-theory twisting that was just discussed. Well, which maps into, by a determinant map, well, not really determinant, maps into BGL infinity of KU, which, well, the units in this are, let's just say it maps into GL1 of K of KU and hence into pic of K of KU. Just because GL1 of this, well, it looks like the units in Z and this space with its multiplicative structure. In other words, it's using this equivalence. This is the units in Z cross BGL KU, maybe tensor. Yeah, well, you should think of GL1 of KU as the KU linear automorphisms of KU, or the units in the infinite loop space of KU. The multiplicative, the invertible elements in the infinite loop space. Okay, and I guess I'm out of time, but I wanted to do a fourth example, which will just take 1 minute, which is the example of a Tia duality. So if M is a closed, well, let's just say a compact manifold with tangent bundle T, then I can construct this map M to BO, which I'll call minus T, the stable normal bundle. Which maps into BGL1 of S, and hence to pick S. And the Thom space of this, so I guess I'm going to write it as m to the minus t, the Thom space of this map is, as is well known, the dual of the Spanier-Whitehead dual of the suspension spectrum of M. But this actually follows formally from this abstract machinery of this Wertmüller context and the fact that, well, since M is proper over a point, I have a dualizing complex. And you can calculate it to be basically, well, not quite this, but as a sphere over M, it's the tangent representation sphere. And I'll stop there. Thank you.